In the first video we covered the working principles of a semiconductor. In this PV1X recap video we will take a look at the p-n junction. When a p and n-type material are connected, the enormous concentration gradient and mobility of carriers will cause them to diffuse. Holes will diffuse from the p-type crystalline silicon to the n-type crystalline silicon and the electrons vice versa. The electrons and holes will quickly recombine with each other. This results in an interface region that is depleted of the free electrons and holes. Since the ionized dopant atoms are fixed in the crystalline lattice, this leads to electrostatic charge built up in both the p-type and n-type silicon. The p-type region near the interface after the depletion of holes will be negatively charged and the n-type region positively charged. The amount of charge in the p-type region is proportional to the acceptor concentration, and the amount of positively charged in the n-type region is proportional to the donor concentration. When there is a net charge present in the depletion region, there must be an electrostatic potential difference between the edges of the depletion region. We call this electrostatic potential difference the built-in voltage of a p-n junction. This built-in voltage is clearly visible in the band diagram of the junction, where there is a difference between the position of the energy levels of the conduction and valence band edges at the opposite sides of the p-n junction. The position of the energy levels can be influenced by applying an external voltage. In PV1X we have shown and discussed how the p-n junction behaves under forward and reverse bias. By applying a forward bias we can obtain the JV curve of the illuminated p-n junction. The JV curve is generally obtained under standard test conditions. From this curve we can determine the most important external solar cell parameters. The short circuit current is the maximum current that flows in a solar cell when short-circuited. The short circuit current is the photo-generated current. The open circuit voltage is the maximum voltage generated at the electrodes of a solar cell. We can measure the open circuit voltage when terminals of a solar cell are not connected. To find the maximum power point, we can plot the power voltage curve. From the ratio of the peak power to the product of open circuit voltage and short circuit current, we get additionally external parameter that is called the fill factor. The fill factor, the open circuit voltage, the short circuit current density, maximum power point and efficiency are related according to these equations. Finally, by determining the slope of the curve around the open circuit voltage and around the short current density, we can find the series resistance and shunt resistance respectively. We'll get back to this later. So far we have looked at the junction between two very similar materials, a so-called homojunction. We will now look at the junction between two different materials, such as a metal semiconductor interface. For semiconductors, the definition of the vacuum level is similar as for metals, namely the energy level at which an electron released from the material has no interaction with the semiconductor. Also, for the semiconductor, we can define a work function as the energy difference between the vacuum level and the Fermi level. The Fermi level expresses the electrochemical potential of electrons in the material. Additionally, we have the electron affinity. This is defined as the energy difference between the vacuum level and the bottom of the conduction band. The importance of the electron affinity is that it is a specific fixed material property, whereas the work function of a semiconductor can vary by changing the doping concentration in the material. In PV1X, we have discussed how to form this metal semiconductor junction and seen that if the work function of the n-type semiconductor is smaller than the metal work function, we obtain a Schottky barrier junction. Vice versa, if the n-type semiconductor work function is larger, an ohmic junction is obtained. We have also discussed the concept of thermionic emission and the JV characteristics of metal semiconductor junctions. The final junction we discussed is the one between two different semiconductors. Shown here is a straddling type heterojunction with a low bandgap n-type and a high bandgap p-type semiconductor. From this energy band diagram, you should now be able to determine a number of relations. This covers all the semiconductor physics discussed in PV1X and thereby all processes that affect the recombination and bandgap utilization losses in a solar cell. To discuss the other electrical losses, we need to look at the equivalent circuit of a solar cell. Here you can see the so-called single diode model for a solar cell. It has a current source for the photogenerated current and a diode that represents the solar cell diode characteristics in the dark. The diode actually represents the recombination in the solar cell. Next, we see the shunt resistance and the series resistance, which are the source of additional electrical losses in solar cells. The series resistance is caused by the bulk resistance of the semiconductor materials and the metal electrodes and the contact resistance between the semiconductor and the metal. The shunt resistance, on the other hand, is parallel to our load, so it should be as large as possible. A reduced shunt resistance is caused by leakages across the PN junctions around the edges of the solar cells or defects, pinholes and impurity precipitates in the semiconductor material. Recombination, bandgap utilization and the shunt and series resistance determine the electrical performance of a device. In the next and final PV1X recap video, we will do a quick summary of the optical losses in solar cells.